Okay, good morning. Today I will try to finish the lecture about the fluid and the solid particle flow. But before I continue the materials, maybe I will brief refresh what I have explained to you last week. So basically, when particles are flowing together with the fluid, for example, in the gas or in the liquid, there will be differences in velocity. And the velocity in fluid and solid particles, normally we use the terms relative velocity. It's the difference between the particle, the solid, and the fluid. So depending which one is higher, you can always calculate the relative velocity, or sometimes we call it slip velocity, and the value is always positive. So depending on which one is higher. And why we need to calculate the velocity as slip velocity? Because basically the slip velocity will be influencing the Reynolds number of particles. The concept is similar with the Reynolds number of the fluid flow. So Reynolds number is basically comparing, or it is a ratio between the inertial force divided by viscous force. But to calculate the particle Reynolds number, it will be different with the fluid Reynolds number, because the diameter that influence will be the particle diameters, and the density and the viscosity is fluid. This one is also fluid, and the velocity is the slip velocity. And from this Reynolds number of the particle, you can calculate what we call drag coefficient. So the drag coefficient basically is drag force divided by the area, density, and the square of the velocity. And the concept is similar with the friction factor. We can calculate the drag force by using certain equation or using certain graph. For example, for very low particle Reynolds number, the drag coefficient will be inversely proportional to the particle Reynolds number. You can use directly the equation, but for higher Reynolds number, you have to use the graph. This is the simplest things. The easiest way to calculate the drag coefficient will be by calculating Reynolds number, and then you choose the appropriate graph. How to choose? Then you choose the typical shape of the particle, whether it is a sphere or cylinder or maybe a disc or some others. Then you just correlate using the graph, and then by calculating the Reynolds number, then you get the value of drag coefficient. Then after you find the value of drag coefficient, you can calculate the drag force. This is the concept for um, particle that's flowing with the fluid. And then for falling particles means the fluid is uh, stagnant, but the particle or the solid is moving. Then for the falling particles or falling objects, then you can derive the force balance. Force balance consists of the weight balance, weight force, then buoyancy force, and the drag force. The weight force will be in downwards direction. This is the weight force or external force. It can be influenced by gravitation, hence the name is the weight force, but it also can be influenced by the centrifugal force. So this is the downward direction, but the buoyancy is upward, and the drag force is also upwards. So from this force balance, you can derive the accumulation of velocity or the change of velocity of time. Then from the change of velocity of time, this one if it's the gravity, and this one is for the centrifugal field, you may calculate the what we call settling velocity or terminal velocity. When a falling object reaches the terminal velocity, it means the velocity become constant. There will be no change in the velocity, so du over dt will be equals 0. Then you can calculate you can get the equation to calculate the terminal velocity or settling velocity. Okay. From the equation of terminal velocity, uh, of course, you can get the value of the velocity, but the velocity itself will be depending on the drag coefficient. And the drag coefficient is also a function of the velocity. So there will be some iteration that you need to do to obtain the value of the terminal velocity. Okay. Calculating terminal velocity can be simplified if the Reynolds number of particles follow certain value. For example, if the particles are spherical and the Reynolds number is very, very low, then you can get the drag coefficient will be inversely to the Reynolds number. This is this one, right? Then this one is the terminal velocity. Then you can get this equation. But it's only for the very low Reynolds number. Other simplified equation can be used if the Reynolds number falls between 500 and 200,000. For the spherical, why this is the special case? Because in this range between 500 until 200,000, the drag coefficient is 0.44. Then you can simplify the equation. You do not need to do the iteration. But if it's not below 0.2 or not between 500 or 200,000, then you need to do the iteration as we can see from the exercise. Okay, have you done the exercise? Sudah dicoba? Have you tried the exercise?
Belum sempat, Sir.
Okay, maybe I try to finish the material first because it's only left a bit. Then we can do the exercise later. Okay, the equation that we have learned so far is only for the single particle. What does it mean when we try to derive this equation? This one. Yeah. This one, we analyze single particle. From this single particle, we can derive the three types of the forces, right? FB and the drag force. How about if we are dealing with the many particles, or we call it concentrated particles? It means not only one particles. The phenomena is like this one. All particles are falling. First, the size of the particles, each particles might not be the same, right? The size of the particles might not be the same. The shape might not be the same. So it means the weight force, the acceleration force for each particle is different. And then the buoyancy force or also the drag force will be different. And what will happen when more than one particles, or we call it concentrated particles, are falling? The velocity gradient of each particle is basically or Yeah, the velocity gradient of each particle will be affected by surrounding particles. So it's not only influenced by the weight force of the particle itself or the physical condition of the fluid, but it will be addition of particle interaction from the surrounding. Okay. So when we deal with the concentrated particles, it will be very complex. The derivation of the equation will be very complex because the normal drag force correlation for one particle will be not valid. Like you cannot just calculate the weight force for each particles and then do the summation of all the forces. But since there are some interaction between particles, then the velocity gradient of the particles of each particle will be different. The time when each particle reach terminal velocity will also be different. And what happened with the concentrated particles? Because a lot of particles are falling down, the movement of the particles may cause the fluid to flow. If you just consider one particles falling, we can assume that the surrounding fluid is not moving. But if you consider a lot of particles are falling down, then some of the particles may cause the fluid to flow. So the particle relative velocity or the slip velocity will be different with the single particle falling. That's the phenomenon. That's why we can derive some simple equation only for special cases. For example, if you have just two particles uh, for this uh, for this lecture, we just will deal with this some simple equation. So for if you are just dealing with the two spherical particles, in laminar flow, it means the Reynolds numbers is below 0.2, and then the diameter of both particles are the same, but the density of the particle are different. Then you can take the ratio of each terminal velocity by take account the differences of the each particle density with the fluid density. How to get this equation? Basically, deriving from the mass balance of each particle. And then, if you have two different particles with different diameters, but the same density, then basically the ratio of the terminal velocity will be the quadratic ratio of the diameter. And then two particles will have same terminal velocity or falling velocity if you have the so it means two different particles, right? With different, this one, so the density is different and the particle diameter is also different. Then two particles will have same falling velocity if the ratio of diameter following this equation. This one is for laminar, this one is for turbulent. So these three cases of concentrated particles, this is the simplest case. Okay, the application of falling particles is basically this principle is used by the viscometer. By the name, you can guess, right? What is viscometer? Viscometer is device that is used to calculate viscosity of certain liquid. So basically, you have a tube arrangement, and then you put a spherical ball inside the tube, and then uh, you calculate the travel time for the ball reaching from uh, top area to the bottom area. So the liquid that you need to measure, the viscosity that of the liquid that you need to measure, you put inside the tube, and then the ball will falls in the liquid, and uh, by making sure that the particle Reynolds number is 0.2, it means the size of the ball is very small, and then the falling velocity you can calculate, right? The falling velocity is the length of the tube, this one, this one. So this is the L, and then the time is t, and then you can calculate the falling velocity will be L divided by, then by using the Stokes equation, then you can get the value of the viscosity, because you already know how much is the density of the ball or the particle, and then how much is the density of the liquid. You calculate the time, you calculate you have the value of the length, and then you have the value of the particle diameter, then you calculate the viscosity. This is one example, the application of the falling particle concept. Okay, until this one, do you have any question?
So far, okay, sir.
Okay, actually this is the end of the slide. Later you will have application of particles, especially for the unit operation that we use in chemical engineering with Pak Anggit on this Thursday. Okay, so for this is for the for the exercise, you have particle diameters, this one, and then the temperature of the air. So the fluid is air. The temperature is 294.3, and the pressure is this one. So by using the ideal gas law, you can calculate how much is the density of the air. Okay, then the density of the particle, this is the density of the air, is 1280 kilogram. Okay, now first we want to know the terminal velocity. Terminal velocity, the basic formula is this one. Oh, this is, but this is key, right? Which one is the equation? Okay. So this is the basic formula of the terminal velocity. But sorry, I 4 dp rho this is the equation, right? Okay, to calculate the terminal velocity, first you need to calculate the CD, the coefficient of drag. Then CD itself is also function of the terminal velocity. So how to solve these problems? Basically, first you can first assume the Reynolds number is fall in this area, which is CD is 0.44. Okay, have you calculated by using this assumption? What is the terminal velocity if you put the value of the drag coefficient is 0.44? Berapa? How much is the UT in meter per second? First, please calculate the density of the air in this condition. Please do the calculation if you haven't done the calculation. Atau sudah ada yang menghitung?
Bentar, sir.
How about the other student? Have you done the calculation? You remember the MR of air?
Sir, kalau misalnya itu row of water ya, sir?
Sorry, this row of, because the dust particle is falling in the air, right?
Air ya, berarti 1.2 ya, sir?
Is it around 1 point? You need to calculate first using the PNT data, but it should be
Oh my
around 1.
god.
Yes.
Okay.
You can use the equation on the very first slide, how to correlate the density of the fluid with the pressure and temperature using the ideal gas law. So this is density, right? So density will be pressure times mR divided by R times T. Don't forget the unit of mR, the molecular weight, will be in kilogram over mole. Should be converted into kilogram per mole. And R is 8.314 joule per mole Kelvin.
I got 1.2, sir. Bener nggak ya, sir?
It should be okay. The value is around 1, right?
Yes, sir.
Try to put the value of drag coefficient 0.44 into the terminal velocity equation and check what is the value of the terminal velocity. How about others? Have you got the value?
Terminal velocity-nya I got 1.4, sir. 1.4
4.
meter per second. Is that
Okay.
right, sir?
Then please calculate the Reynolds number then. The Reynolds number is
Okay. Sir, is the viscosity given, sir?
oh yeah, it's not given. Then you can use viscosity of air at normal condition at room temperature because it's near room temperature.
Cari di Google, sir.
Yeah, or you can use the text. Let me find it.
18.6 benar nggak, sir? Viscosity-nya.
15.
18.6, sir.
In the standard unit is Pascal second, right? So it should be very small. Should be
Sorry, sir. It's 18.6 micropascal second, sir.
yes, yes.
Okay. Okay, sir.
So around 1.8 times 10 to the power of minus 5, right?
Yes, sir.
Okay, the mu is 1.8 times to the power 10 of the power of minus 5 Pascal second. Hopefully you get the Reynolds number between 500 and 200,000.
Sir, it's 5,780, sir.
5,000.
Yes, sir.
Then should be okay.
Yes.
Okay. So this one is still not iteration case, right? Because when you put the drag coefficient is 0.44, the drag coefficient of 0.44 is for sphere that with Reynolds number between 500 and 200,000. Then when you input, but please recheck your calculation. When you put into this equation, you get the terminal velocity is 1.4. And when you calculate into the Reynolds number, you get how much? 5,000. So the drag coefficient is still 0.44. But if you get the Reynolds number is below 500 or above 200,000, then this you can use this one. If above 200,000, and then replace the 0.44 into 0.1, sorry, then put into the equation of the terminal velocity, you get the new value of terminal velocity, then you recalculate the Reynolds number. If it's still above 200,000, then it should be okay. Okay, any question?
All good so far, sir.
The calculation for the basic particle flow is basically is only calculating the terminal velocity, whether it's calculating the terminal velocity or you calculate the viscosity of the liquid by using the principle of the viscometers. Just any of these two. Okay, if there is no question, then I can stop the lecture. Do you have any other question regarding the materials? Later, Pak Anggit on Thursday will explain about the application of the particles like infiltration, fluidization, or in what else? I forgot the name of the units. I think there will be 3 types of unit operation that will be discussed in the next class. And then we will continue with the mixing phenomenon. Okay, do you have question? So far, okay or confusing? I hope it's okay, right?
I'm okay, sir, so far.
But the others so quiet. Any question from other students? Can you do the attendance? I have changed actually from 1 p.m. into 10 a.m.
Yes, sir, I signed up already, sir.
Okay,
I marked my attendance already.
okay, there should be no problem with the 6. Okay, if there is no question, then I'll stop my lecture for today. And then we will meet again maybe next week after Pak Anggit give you the application of the particle. Thank you and good morning.
Thank you very much, Pak.